All right, guys, today we're going to model direct variation. It's kind of a continuation on slope-intercept form, kind of an application for it. So shouldn't be too bad today. Let's see what we can do. First of all, direct variation is this equation, y equals ax. Sometimes books use y equals kx, and the way you read it, you say y is said to vary directly as x. A, which sometimes is k, is called the constant of variation. It's going to be the same all the time. It's constant and never going to change. It's kind of like we were using slope, and now with direct variation, we call it the constant of variation. The graph of a direct variation is easy to find. It has a slope a, the constant is the slope, and the y-intercept is always 0. That's key. So the graph's going to look like that. In that case right there in that picture, 1/2 would be a, -1 of the blue line would be a, that's the constant. And notice they both go through the origin because the y-intercept must be 0 in a direct variation graph. All right, they're going to give you 3 or 4 kinds of problems today. The first type says write and graph a direct variation where that is a solution. Remember that a direct variation equation looks like this, y equals ax. All you're going to do to find out what the equation is plug the point in. So 8 is the y coordinate, -4 is the x coordinate. Divide both sides by -4, and what that gives you, it gives you -2, but that -2 is your constant of variation. So our equation is y equals -2x. And what they want you, that is our equation. That's one of our answers. That's the direct variation equation. They also wanted you to graph it, so I'm going to draw a little graph here. Remember, your graph of direct variation has to go through the origin. So I'm going to do that. I'm going to start at the origin. The constant variation, or the slope, is -2. So I'm going to go rise -2, run 1, get my other point, connect the dots, and there it is. That's all there is to it. Let's go one more of those. This time the point's -7, 4. Remember our equation is y equals ax. Just plug in the point. Plug in the 4 for the y because it's the y coordinate. Plug in the -7 for the x. It's the x coordinate. Do your division. There's your a. There's your constant of variation, -4, 7. So your equation, your first answer is just y equals -4, 7 x. They do want you to graph it. Remember, your graphs always go through the origin. That's your y-intercept. So I'm going to go ahead and put a point at the origin. Slope this time is -4, 7. So I'm going to rise -4, run 7. Just like that. Other points right here. Connect your dots. And there you have it. They're going to give you a couple of applications. This one says hailstones form when strong updrafts support ice particles high in the clouds where water droplets freeze onto the particles. The diagram shows a hailstone at 2 different times in its formation. Part A, write an equation that gives a hailstone's diameter after t minutes. If you assume the diameter varies directly with the time. So part A, the diameter varies directly with the time. So it's going to look just like that. I'm going to use this bottom picture because I know both numbers. The diameter is 0.75. The time is 12 minutes. That's supposed to be a 12. So I'm just going to divide both sides by the 12. Get my calculator here. 0.75 divided by 12 and get 0.0625. That is my constant of variation. So my equation is this. The diameter is 0.0625 times the time. Now, in this time, in our second equation, it says, okay, what is the diameter? Predict the diameter after 20 minutes. So all you have to do is put the 20 in for the time because it's 20 minutes and minutes is time. So just take those two numbers and multiply on your calculator times 20, and you should get 1.25, and that is in, what's the diameter measured in inches? 1.25 inches. So they are going to have you do some of those today where you have to find the equation first and then plug in a value to figure out what D would be. And the last slide. It says great white sharks have triangular teeth. The table below gives the length of a side of a tooth and the body length for each of the 6 great white sharks. Tell whether tooth length and body length show direct variation. So if they show direct variation, that means they all have the same constant variation. I want you to show you something right here. Here's our equation all day long. Y equals ax, where a is the constant of variation. If that is true, that means our constant always equals y over x. It always is y over x. Now this says that, let's see what they're wanting, just how they're related. So what I'm going to do is I'm going to make this row be my y and that be my x, since that row is a little bit bigger. So I'm going to say 215 divided by 1.8 to get the constant variation, and it's like 119.4. So I'm going to keep going down the row a little bit and see if the constant is really the same all the way down. This is 120.8, so it's really close. The next one, 350 divided by 2.9. Again, just trying to see if they're all the same. This is 120.6, so it's still really close. Let's go one more here, or a couple, divided by 3.6. That's 119.4 again. So these are really close to each other, which means the constant really looks like it is a constant. If it wasn't a constant, I'd be getting different values, but constant means it stays the same. One more here, divided by 5.8, and I got 119.8 again. So all those are very, very close to being the same value. And because they're that close, we're going to say, okay, yes, it is a direct variation. There's a direct variation between the two, which means since the K, or since our A was about 120, that means if the tooth length, let's say you find a tooth on the beach of a shark, you can multiply that by 120, and that's how big the shark is. How much times bigger? It's 120 times bigger, because that's what our constant was. And that's how that works. Hopefully that video made some sense. We'll work on it in class like we always do. Look forward to seeing you tomorrow. See you. Bye.